Hi class, welcome back to Electromagnetics. We want to continue our discussions on analysis of propagating electric and magnetic fields. Last time we set up the current sheet, which was our beginning point, and we want to continue that today to start to set up the magnetic field that should be adjacent to that sheet. First, though, I want to look at another historical background. Again, we're looking at individuals who contributed greatly to the field of electromagnetics. So this person was educated at the University of Göttingen, actually originally in theology, but he was a contemporary of Gauss. So Gauss was a professor at that college at the time, and he noticed that this individual was extremely talented in mathematics, and so he persuaded him to switch over to math, which was actually much to this person's parents' dismay, because they wanted him to be a theologian. I studied at the University of Berlin. He went back and worked at the University of Göttingen or Göttingen. This is an image of the person. Maybe he's familiar to you. His name is Bernard Riemann. So Riemann's actually one of my favorite mathematicians because he did some pretty amazing things and set up a lot of the groundwork for what Einstein was able to do later. What are some of the notable things of Riemann? Well, he developed Riemann geometry, again, which laid the groundwork for Einstein's theory of relativity. He was the first to document the idea of using higher dimensions just to describe physical reality, and this was much at the persuasion of Gauss. So Gauss had kind of figured a lot of things out. Many people think already, or had at least gone down the path pretty far, and so he encouraged his student Riemann to take it further. One sad note about it is, though, that it got so complex sometimes, and it was, it was so difficult to think about these things that it actually drove Riemann crazy a couple of times. He was actually admitted to mental institutions to help him kind of get his thoughts back together so he could continue his work in mathematics. But he did prevail in the end, and he developed a lot of our modern-day complex analysis. If you were to take a course in complex variables, you'd learn about Riemann surfaces and then also conformal mapping, both very powerful tools in mathematics today. Thought I'd expand just a little bit on Riemann because he is so interesting. Talk about some things, probably the most important thing is, I'm not sure if you're aware of the millennial problems in the year 2000. They introduced a certain number of problems that if you could solve them, you'd win $1 million. They put up the cash for it. Riemann owns one of those, and it involves Riemann's zeta functions. So this is a kind of a little bit of an oversimplification of a zeta function, but this is pretty good for this discussion. Whereas zeta of s is just 1 over s plus 2 over 1 over 1 to the s plus 1 over 2 to the s on out for infinity. So, for example, if we let s equal 2, that would be 1 over 1 squared, 1 over 2 squared, 1 over 3 squared on out, and so you could work that out to infinity. This has been solved actually and has a pretty amazing answer, which shocked a lot of people. The answer comes out to be pi squared over 6, and so many people were shocked to see an irrational number, exact irrational number used in the solution. But there's YouTube videos on that to show what that means graphically and how you solved it. And if you're interested in that, you might look those up. So anyway, back to the problem at hand. Let's say we'll set s equal to -1. Well, if we plug in -1 to the zeta function, you can see we just get the summation of all natural numbers. Riemann noted that we could use complex numbers as well as that of, as long as the real part was greater than 1, the series would converge. And so that was a pretty amazing finding that he came up with. He also noted that at s equal 1, there is a singularity here that causes some problems. And he also noted that this above series converges at -1. We'll talk about that in a later slide. But now for the $1 million question. So since Riemann zeta functions are in essence just polynomials, you can see that this is just a polynomial. It's kind of a strange one, but it still is. That being the case, then they must have zeros, that is, values of s which give a result of 0. So Riemann noticed that there were some obvious zeros that all the negative even numbers cause zeta functions to be zero, but more importantly, there's others. Of course, the question was, is there other? Yes, and they are incredibly interesting. According to Riemann's hypothesis, though, all the remaining zeros, other than the trivial negative even numbers, had a real part that was 1/2. The imaginary part could change, but the real part was always 1/2. And he went on to find out there's many, many, many zeros. And so looking at this graphically, here's your trivial zeros out here, -2, -4. But everything else had to be on this line where the real part's 1/2, and so the complex part was what takes us off this real axis. So this is the critical line. So the challenge is, we don't know if there are any more than this line. So far, everyone we found, other than the negative even numbers, have fallen on this line. And so if you can find one that is not on this line nor a negative even, then, and you can demonstrate it and prove it, then you're going to win $1 million. Likewise, though, if you can prove that the rest of them have to be on this line, you also win $1 million. So that's nothing to it, right? Easy. So why is this so important, and why were they willing to put up $1 million for this? Well, Riemann went on to show that there is a direct correlation between the distributed zeros on that critical line, that is where the real part's 1/2, and the distribution of prime numbers. In other words, the zeros of the zeta function between 1 and 100 on that line directly correlate to the prime numbers between 1 and 100. So in a sense, if you wanted to know how many prime numbers between here and 1,000,000, you could plug 1,000,000 into this and it would tell you how many prime numbers you would expect to find. And the crazy thing is, no one knows why. We cannot figure this out. We think that if we could prove that they all lie on that line, that might give us some insight as to why this happens, but so far no one's been able to figure this out. So back to our lecture. We continue on in part 4. Last time we set up the infinite plane current sheet. This time we want to talk about the magnetic field that's going to be generated by that current sheet. So from the previous section, we introduced the idea of this infinite current sheet, as shown here to the right, with evenly distributed current density defined by this equation. So hopefully you remember this from before. We now want to determine an expression for the electromagnetic field that is generated from this current sheet. We now should be able to understand from Maxwell's equations that if there is current flowing, that that is going to generate a magnetic field. And so from what we've learned to this point, the way that we want to do this is to apply Maxwell's equation. So in particular, we need to apply Faraday's law and Ampere's law simultaneously. So since the current sheet that we have defined only has an x component, the current density, it's independent of x and y, this is going to greatly simplify things for us. So Faraday's law is going to simplify to this because we only have this x component, which should generate a corresponding y component. And Ampere's law, again, that should mean we have since this is only in y, our magnetic field is only going to be in y, and then our current is only going to be in the x direction. So greatly simplifies what we're dealing with. And the first thing we want to notice is that in the second equation, Ampere's law here, that on the right side of the equation, the current density term only exists in the xy plane, that is when z equals 0. Once we get off z equals 0, this term right here goes away, so we will not have any current density except on that sheet. So again, more simplification. So again, this now simplifies the equations even more, which now gives us Faraday's law here, and then Ampere's law here, and hopefully from what we've seen so far, this should make a little bit of sense and look familiar to you. So for this simplified special case, these are the equations that must be solved simultaneously to find the expression for this propagating wave generated by our hypothetical current sheet. So this will be our guiding light here. We'll keep coming back to these to make sure that both of these equations are solved at the same time. So how do we do this? Should be easy, right? These are nothing but differential equations. So we've had differential equations, so we should be able to figure this out. So to help us get a start on simultaneously solving these equations, we need to first consider the surface current on our infinite current plane and from this find the magnetic field generated immediately adjacent to the current sheet. So we can do this again here by applying Ampere's law in the integral form. So remember, when we're dealing with systems, so this will be the whole area outside the sheet. So that is a system of view. We need to use the integral form of the equation. So we recall from previous lectures that just says if we form a contour, the magnetic field along that and in the direction of this contour or path has to equal to the current penetrating the surface created by the path. So in this case, we're going to create this path here where we take a slice in the YZ plane or parallel to the YZ plane through our current sheet. So we kind of penetrate the current sheet, come over here, penetrate again, and come through here. So we apply this equation then to this closed path A, B, C, D, A. So you see A, B, C, D, and then back to A. And then we can use this to calculate out H, or the magnetic field, around the path, one segment at a time. And so hopefully we should notice that since the magnetic field is in the Y direction, we've already determined that from the previous slide, that this path here and this small path here are going to, by definition, be zero. And we'll look at that in a minute. So we're going to start by evaluating the left-hand side of the above equation, which is the magnetic field around that path. And so we're going to break this down into 4 integrals. So from A to B, B to C, C to D, and D to A. So looking at this, and we examine it closely, just like I said before, the sides BC and DA, that dot product is going to be 0 because they are not in the same direction as the magnetic field. So this part and this part here should by definition go to 0. So this leaves the first and third integrals, and those are going to be equal to simply the HY, which we know it's only in the Y direction from A to B, times the length AB, and then HY in the CD direction times CD. We do negate the sign here because it's in the opposite direction. So this means that the integral around the closed path then can be expressed here. So we have the difference in these two guys here, but because one of these is negative, that makes that a positive, so we could just say it's essentially 2HYAB times AB, because HYCD is equal to the negative of HYAB, and their magnitude should be the same because it's an infinite current sheet. So this gives us the expression for the left side of Ampere's law. We now need to take a little closer look at the right-hand side of the equation. So in this case, we already have an expression for the current density, J, and the second term is 0. So with an expression for the left-hand side in hand, and now examine the right-hand side, we immediately notice that the D term is equal to 0. So if we plug all this in now, the left side we have 2HYAB. This is our original equation for the current sheet. So we can cancel out the AB terms, and so this now gives us an expression for the magnetic field along this line here in terms of our current sheet density. And so when we rewrite that, we can do it in terms of HYCD as well. That just changes the sign because they're going to be equal but opposite. So one magnetic field's in this direction, one magnetic field's in that direction. So now we have an expression that will describe that magnetic field generated by the infinite current sheet. We have 2 equations, and they are HYAB and HYCD. So one's on the positive Z side and one's on the negative Z side of the current sheet. So we're looking at this here. So one's on this side of the sheet and the other's on this side of the sheet along the Z axis. So if we're to take a side angle view down the Y axis straight down it, so you can see that this magnetic field is coming out towards us. That's the tip of the arrowhead, and the magnetic field on this side of the current sheet is going into the sheet. That's the tail of the arrowhead. And so we've defined our current sheet. Now we've defined, or we've come up with expressions for our magnetic field just outside the current sheet. So this will springboard us into the next steps that we're going to use to continue to develop these equations for this propagating field, which we'll continue to look at in future lectures.